This is lecture 18, chapter 9. And in this lecture, I want to continue discussing moments of inertia, which we talked about in lecture 17. In that lecture, I gave you an overview of what moments of inertia are and where they came from. And in this lecture, I just want to focus on doing a few examples. So the examples will involve usually finding the centroid and then finding the moment of inertia. So as you may recall from the last lecture, that just being able to find the moment of inertia about an axis is fine, but or about the centroid, but most of the time you have to use the parallel axis theorem because the axis of interest isn't necessarily going to be about the centroid of your object. So in this example, we have a simple geometry of a box with part of it cut out. And there's two ways you could do this, just like with the centroid. You could either make it into three pieces, the two top boxes as one piece and two pieces, and then the bottom is a third. Or you could take the moment of inertia of the entire 5x6 rectangle and then subtract out that empty space. So either one works, but let's go ahead and go through that and I'll show you how we do this. So here what I've done is I've drawn the actual structure. And again, we want to find the moment of inertia about Ix prime, which means that we want to find the moment of inertia about the centroid. Now the centroid of this entire object, not of one particular. So what we're going to need to do first in order to do that is we have to find where is the centroid of this object. And I know you've had a lot of practice with that. And so for this one, we'll go ahead and do that real quick. And we can see that if I label these, if I label these as 1, so I'm going to do is I'm going to do this and this. So I'm choosing, excuse me, to say this is section 1 here. This is section 2. And this is section 3. All right. And so as with trying to find a centroid, we first want to find the area of each area of each section. So we know that section 1 is 2 by 6, so it's going to be 12 inches squared, and the other one are going to be 1 by 3, so they're going to be 3 inches. And then if we look at y bar with respect to the x-axis, and again, we're only concerned with y bar, and that's because we're going to find the moment of inertia about the x-axis. If we were trying to find the moment of inertia about the y centroid, the IY centroid, then we would have to find the y centroid. Now, in this one, it doesn't matter because this is a symmetrical, so the y is 0. We can see that. But if, say, the origin, if this was not symmetrical, we'd have to do that. But again, if we're only looking for, if you see find Ix, then all you need is y, and I'll show you that. So we know that the centroid of this, if this is 2, then that's just going to be 1, because again, the centroid of that piece. And then we know that for this piece, it's the centroid is half of 3 or 1.5. So 1.5 plus this 2 gives us 3.5 and 3.5. So now we multiply through, we get 12, 10.5, 10.5, and we sum that, that's 33. We sum this, that's 18. And so we know that big Y bar now is just equal to 33 over 18, which equals 1.833. All right, so that's the important number that we need in order to find the moment of inertia. So I know that the centroid now of this entire object is aligned somewhat like this. So this is now the axis x prime that I'm looking for. And so that's the line. And so we don't really care about the y location because we're rotating about x. So that means we're going to have to relate the rest of these three pieces to that using the parallel axis theorem. So how do we do that? So first off, when we're doing, we split them up into different pieces. So we know that this is our first piece 1 here. And so we know that our equation, ix1 for this, is going to be equal to ix1 prime plus ad squared. So remember, with the parallel axis theorem, we always have to take the moment of inertia about the centroid of that piece, which in this case is just this 2x6 rectangle, and then add the ad squared to it. So in that context, it's going to be ix prime, so that's just going to be 1 over 12 times the base 6 times 2 cubed, and that's going to equal 4. All right, so we know that this equals 4, okay, and we know it's 4 inches to the fourth. And then we're going to add to that the ad squared. Now we know the area of that piece is 12 because we found that up here. And then the distance is essentially the distance of the centroid of this piece to the centroid of the overall piece. And so if we know that this is 1.833 and this is 1, right, it's going to be 1.833 minus 1 squared. All right, and so, and notice that because it's squared, it really doesn't matter which one you subtract from. So we know this distance, again, is 1.833. If we know that this distance here is 1, then we're just looking for this difference right there, which is 0.833 in this case. So we have that, and that ends up giving us, if we multiply this by this, we end up with a number 8.33. So this is 8.33. This number here, all of this together. And so if we add those together, we get about 12.33. So this whole thing equals 12.33 inches to the fourth. So that is my ix1. So let me just write this a little better. ix1 equals this. All right, so that's the first piece, that's this. So effectively what we need to do then is find it for 2 and 3 and then add them all together. Because 2 and 3 are the same, if we find 2, we can just multiply it by 2, or find 3 and multiply by 2, doesn't matter because they're identical. So in the next case, if we look at, we'll say ix2 down here, then we know again that that's going to be 1/12, again, the equation, sorry, we know is ix2 prime plus ad squared, right? So that's always the case because unless the centroid of the object goes through the centroid of the small piece, then you have to use parallel axis theorem. So again, this is just the moment of inertia of that piece, number 2, plus this additional ad squared from the parallel axis theorem. So if we do ix2, we know that that's going to be 1/12 1 times 3 squared, right? Because it's the base is 1, the height is 3. And so that just gives me 2 1/4. So I'll write that down there. So I have 2 1/4. Now I have to add to that the ad squared term. So area is 3. So this is going to be plus 3. And then the d squared, what is the d squared? Well, we know that from the middle here down to this distance here, we have what? We have 4.5, sorry. We have all the way up here to the middle, that's going to be 4.5, right? Because it's 2 plus 1.5 to the center. And this is 1.833. So we want the distance here to here. So if we do 4.5 minus 1.833, sorry, I meant 3.5. Yeah, that's 2 plus 1.5 is not 4.5, 3.5. So 3.5 minus 1.833, and that's going to give us a value of 1.667. So we have essentially 3.5 minus 1.833 squared. All right. And so that gives us a total of 8.34 roughly, that. So now we know that we add that together, that's what, about, and a quarter, so it's about 8.6, 10.6 roughly. And so what we're going to do now is, so we know it's 10.6 inches to the fourth, and then we're going to multiply that by 2, right? So because we have 2 of these sections, we have this one and this one, and they're both the same in terms of their moment of inertia value. So what we end up with then is we end up with a total of about 33.5. So we get 12.33. We get a value about 33.5. So we have essentially IX1 plus IX1 plus IX2 plus IX3 equals IX total. All right, and that's the prime. We've got to keep that. So these represent each individual ones. And so if we add up the basically 12.33 plus 2 times 10.6 roughly, we get a total of about 33.5 inches to the fourth. And you can check my work, but that's what it should come out to. So that's that. So hopefully that made sense. There's different ways that you can write this out. In some examples, they will literally write this out like they did the centroids, where they'll write out a column for A, a column for the IX prime, a column for dy, a column for the A dy squared, and then they'll add them all together. So that's that example. So let's go and do another one. And after a few, I think you'll get the gist of it. So here's another example, and this one is similar in the sense is that you have 3 different shapes that you need to find, and then you're going to, and in this one, we're going to find it about both the X and the Y axis. So what we have is this structure, the 1.3, 0.5, 3.6, so forth. So we'll start off in that, and you should have the example hopefully printed. So you get something that looks like this, all right? And so in that context, I've put the dimensions in here. So 1.3 wide, 1 inch thick, 3.8, that's this distance from here to here, 0.5, 3.6, and then 0.5 thick. So you have everything you need. Now, in this one, I've already calculated. I know you know how to do X bar, Y bar, so I've already calculated them for you. So you have 0.912, 2.25, and those are, of course, everything's in inches, all right? So if we go ahead and we draw out our centroid axes, we know that the centroid of this object lies right here. So as you can imagine, if we're going to find the moment of inertia about IX prime, then we're mostly interested in this Y bar, the 2.25 inches that goes up from here, because that's the value that we're going to use to determine our d distance relative to the center of this, the center of this, and the center of that. All right, so let's go ahead and write a few things down and get this problem started. So here's the general equation. So ix prime equals ix1 plus ix2 plus ix3. And that's just, so we know we have to add all that together like in the last one. Now, for ix1, we know then that is going to be ix1 prime plus ab squared. And these primes get tricky, but what this is saying is that for this piece here, the moment of inertia relative to this axis is going to be equal to its moment of inertia about its centroid right here, plus the AD squared, which is the distance from here up to there. So what I'm going to do now is go ahead and we'll write in the different distances, and that might make it a little easier to see what's what. So I've drawn these in, hopefully they help. So this shows you the distance D1 from here to here, the distance D2 from here to here, and the distance D3 from here down to there. So in the equation then, when we do this, we're going to have ix1 equals, so I'm just writing it next to it for space, going to be 1/12 and then 3.6 times 0.5 cubed, because that's the height of it, right? So 3.6 is the base, 0.5 cubed, so we get that, and then plus the area. So the area, 3.6 times 0.5, that means it's half, so it's 1.8. I can put inches squared just for clarity. And then again, all this is inches. So that's my A, and then my D squared is just this distance here. So that would be 2.25 minus 0.5 all squared. So the 2.25 being this, and again, it's all we measure relative to the x-axis, and that being the 0.5. We get that, okay? So this gives me a essentially 0.0375, not very big, plus 7.20 for a total of 7.2375. So just keeping a few extra decimals, but that's that. So this plus this. So that's ix1. So let's go do ix2. And so for that one, we're going to have, and I'm not going to write the equation. We know it's still going to be ix prime plus AD squared. So I'll just put in the ix, the centroid for this section. That's going to be 1/12, and then the base, in this case, is only 0.5 thick. The height is 3.8 cubed, and then that's going to be plus the area in this case, 1.9, because 3.8 times a half inches squared, and then the distance. So this distance here, the centroid, is going to be half of this, or 1.9 plus 0.5, which is 2.4. So 2.4 minus 2.25 squared. And so that, all of that added together gives us 2.3291. And you can round during when you're doing it, but that's that value. And then we do the next one. And this is part of I'm doing this is to keep this on everything on the page so you can see the diagram. So ix3, same thing, only now we're dealing with this top shape. So we know it's 1.3 wide and 1, right? So it's going to be 1/12 times 1.3 is the base, 1 cubed is the height, plus, and then the area, of course, 1 times 1.3 is 1.3 inches squared. And then our distance, D3 from the bottom, ends up being a half plus 3.8 plus another half. So it's 4.8 from the bottom or from the x-axis. And then that's going to be minus 2.25. And again, it doesn't matter which order you're squaring it. So if it ends up negative, it doesn't affect it. And so that answer is 8.5616. And so if we add it all together, we get 18.13. And so Ix about the centroid is equal to 18.13 inches to the fourth. And that should be how you present your answer, because 4 sig figs leads with the 1, inches to the fourth, proper units, and there you go. So we're not done yet, because we also want to look at this as what happens if we do it about the y-axis. So I'm going to hold this. And so with the y-axis, we kind of think of it as now we've turned it this way. And so our y-axis is here. There's our y prime. So we know we're given 0.912. That's this distance here. So we essentially do it the same way. The only difference is everything's kind of rotated. So if it helps to rotate the paper, do so. So we're going to do the same thing. We're going to carry through. I'm going to put that up there. So what we'll have is y prime equals y1 plus y2 plus y3. And then we know that y1 is equal to, now it's going to be, it's going to have the same y prime plus 80 squared. So if we put the numbers in, we know it's going to be 1/12. Now for this, the base is now what? It's 0.5. And now the height is 3.6. So base is this, and the height is that. And then 80 squared. So the area is still the same, 1.8 inches squared. And the distance now is half of this centroid is 1.8. And then we have to subtract it from x bar. So 1.8 minus 0.912, all squared. And so this total is 3.363. All right. So let's do the next one. So then we have y2. And so same idea, 1/12 for the base. And that one has the area of, or I'm sorry, the base is 3.8 and the height is 0.5. And so that's representing this piece here. So 0.5 tall when you're going from this side. 3.8 is the base, 0.5 tall. And you can see on the next one, it's going to be 1.3 tall and 1 thickness or base. So turning it back, we have that, and then plus, now we know the area of this section is 1.9 inches squared, and then we know that it's going to be 0.912. That's the x bar, and then its centroid, because it's only 0.5 thick, it's going to be 0.25 as far as its centroid goes, and that's going to be squared. All right. So that value is equal to 0.8723. All right. So then lastly, we have y3. And that's going to be, again, 1/12. 1 is the base, 1.3 cubed, and then that's going to be plus 1.3 inches squared. And then in this case, it's going to be 0.912. Sorry, not 6. And then we know that if it's 1.3 tall, then half of that is 0.65, so 0.65 squared. So if we multiply through that, we get everything 0.2723. So if we add all that together, we get an I y prime equal to 4.51 inches to the fourth. All right. And so we had the other one, which was 18, and this is 4.51. So significantly smaller. Again, it just depends on how much, and again, it can make sense because it's smaller because you have less material, or actually more material closer to the axis of rotation. Whereas when you look at the x-axis, material, most of it is away from the axis of rotation. So that's a simple shape. So in terms of quizzes or tests, you would be given the, I would expect you to use the equations in your book, and I'd also would only give you simple geometries. So you can see that I could have added, say, a triangle on top of here, and it wouldn't have changed anything. It would have just changed the equation that you would have used in order to find the primary moment of inertia. Okay, so I have one more example I want to show you in this lecture, and it's going to be what I call the ice cream cone. And so we want the moment of inertia about the centroid of Ix. So it turns out that finding the centroid about Iy is a bit more complicated. I'm not going to do that in this example. If there's time, I might, but I'm really trying to just give you the basics of moment of inertia because you're going to be revisiting it quite a bit in future classes. So we look at this one. It has a fairly simple geometry. We have essentially two pieces that we're going to look at. We have the semicircle and the triangle. So we start off with this, and we'll go ahead in this one and quickly find the centroid since we don't know where it's at. And I've labeled the triangle 1 and the semicircle 2. It's 9 inches by 6. And so we know that the area of a triangle is 1/2 base times height. So that'd be 1/2 of 9 times 6, or 9 times 3, essentially. So 27. And we know that the area of a half circle is just pi r squared over 2. And that's going to give us 14.14 roughly. And so if we add those together, we get a total of 41.14. That's our sum. All right. And then after that, we need to find our x bar and our y bar. Now, we know that with respect to a triangle, it's 1/3. So if we look at from x, it would be basically 9/3 or 3 from up here. So that means it's going to be 6 from down here. So my y bar is going to be 6 for that. And my x bar is just going to be 2 because this is 6. So 6 divided by 3 is 2. That gives me my 2. So that was easy. So then I look for my cone here. And for that, I know that for y bar, that equals 4r over 3 pi, which is equal to, if r is 3, the 3's cancel, right? And you get 4 over pi. So if I want to know what y bar is for this, it's going to be 9 plus 4 pi. So y bar is 9 plus 4 over pi, which is just a little bit over 1. So that's 10.27. All right, sorry about that. So 9 plus 4 over pi is my y bar, 10.27 if you add those together. X bar, if I look at a circle like this, if I go, from the orientation of X bar, it kind of looks like this. So it's just going halfway. So if I just go this far in, it's just going to be 3. So X bar is just 3. So I drew this just to illustrate that if you go, this has to be the center of it because it's halfway through the circle, meaning there's just as much material above and below. Same way if you come from this direction, okay? So then just a matter of multiplying through, we get 54, 162, 42.42, 145.3, totals 96.42 and 307.26. And something, yeah, it's 307 point, it should just been 307.3. So leave it at that. Anyway, what we find then is if we divide this by this, we get our y bar equal to 7.47, okay? X bar equals 2.34. We don't care so much about X bar because we're only finding IX, so we really just care about this number. This is the important number here. All right, so we have that. So let's find the moment of inertia then. So what we're trying to find is the moment of inertia about this axis, the 7.47, the centroid. Now we know, again, that we're labeling these as this will be 1 and this will be 2. And if you look in your, so let's just do the triangle first. So if we look at the triangle number 1, we know Ix of 1 is equal to Ix prime plus AD squared as normal. So for a triangle, that's going to be 1/36 times 6 base times height cubed. And so that's our value. So the 6 cancels, and it's basically 1/6 of 9 cubed, which gives me a value of 121.5. And then my AD squared value is plus, and so the AD squared is the area, which we know is 27 inches squared. And then the distance is 7.47 minus 6 squared, all right? So 7.47 minus 6. And that gives me about 58.3. So that gives me a total of about 179.8 with some rounding. All right, so that was the easy one. So then let's look at the ice cream cone, or actually the ice cream of the cone, the top. And if we do that, that's Ix2. And now it turns out that if you look in your book, that you aren't given this equation for the centroid of a semicircle. What you're given is it from this part. So what that means is that if you look in your book, in your table, it's something like this, and it's pi over 8 r to the 4th. And that's your moment of inertia. But when you're using the parallaxis theorem, you cannot use that. So it'd be incorrect to just say, oh, pi over 8 r to the 4th, and then say, well, that's 9, right? 9 minus 7.47 gives me that distance. So you cannot do that. You cannot make this D2. That does not work. It always has to go to the centroid. So we have to then go to where the centroid is. Now we know the centroid location because we know that that height there is 4 over 3 pi, and we found it in the previous problem. But the question then is, what is the equation about the centroid? So what is the moment of inertia? What is Ix prime about it? So actually, it's not a hard thing to derive because to derive it, you can use this relationship here, and you can say, well, I know that Ix equals Ix prime plus AD squared. And if you do that, you would put it would be rewritten as Ix prime equals Ix minus AD squared, right? You just move it to the other side. And so you'd end up with this being pi over 8 r to the 4th. And then you would substitute in AD squared. Well, you know that the area is what? Pi r squared over 2. And you know the distance is 4r over 3 pi squared, right? That's the distance. So if we go on and we simplify this, it's some things canceled. We end up with Ix prime equal to 0.1097 r to the 4th. And this is often just rounded to 0.11 r to the 4th. But if you Google it, you'll probably see this number or the 0.11, and that's where this comes from. So, I mean, if you want to carry this through, if you square it, it becomes 16r squared over 9 pi squared. And then you end up, you factor it out, the r4th, and then the others are just constants, and they reduce to this. So we have that. So what we're going to do up here is we're going to write this as 0.019, 0.1097, and then r to the 4th, which is, the r is 3, and then plus my AD squared. Well, my area was 14.14, and the D, the distance, would be 10.27, because that's the distance we found earlier in the centroid. That's essentially 9 plus this 4 over 3 pi, right? So this distance all the way up to here would be the 9 inches of the height plus this little bit. So that's the 10.27, and then we subtract that from our centroid, which is 7.47. That's squared. All right. So what we end up with then is about 8.89 plus 110.9, or about 119.74. So you can see that that's about 180, that's about 120. So when we add it together, and I may have rounded, or you may have rounded when you're doing it, but essentially when you get done, it's Ix prime is equal to 300 inches to the 4th. And if you have 299.9 or 300.1, it's close enough for government work. And so that's what we have. So hopefully that made sense. I'm not going to give you anything more complicated than this in terms of geometries. Usually even on the final, we might add maybe a quarter circle or a square with some circles cut out. But the idea you have to remember, and this is the big takeaway from this, is if you're doing a moment of inertia, you have to go from the centroid of the shape to the axis of your rotation. So, and sometimes they may just ask you, in this example, it could have been find the moment of inertia about the x-axis. So in that case, then you would have done the same process. You would have just gone from, of course, the centroid of this shape down, and you've gone from this centroid to this, from this centroid down to this line. So the lines are all relative, but the process is still the same. Okay? So that's the three examples I want to show in this lecture. For the final lecture in chapter 9, I'm going to do a couple of composite examples where you would actually look up values in a table, and that's more so how you would do it if you were designing. And then with that, we'll be done with it, and then we'll move on to chapter 6. So thank you.